Welcome, everybody. It's a pleasure to have you all here on another session of Lógicos in Quarentena. And I would like to thank you very much, Professor Daniele Nantes from Universidade de Brasília, who kindly accepted our invitation to give this talk. Dani, thank you very much.
Thank you, Bruno. Thank you for the introduction. I'm going to talk about nominal equational problems. This is a joint work with Maurício Ayala Rincon, Maribel Fernandes, and David Vale. So this is the overview of my talk. So I intend to start giving you some motivation, move to the nominal syntax, to the nominal equational problems, to give you a hint of our rules, and then conclude with future work. Okay, so motivation. We were reading some papers, like old papers from the 80s, and then we read this paper in particular that was written by Coleman and Lescan, where they wrote, an equational problems is any first-order formula whose only predicate symbol is equality. That is, it has the form of this existential of this variable with a forall of some variables of a system P, where P can either be an equation or a disequation or disjunction or conjunction of systems or failure or success. So we started thinking about this problem. This is a first order problem. And this problem is interesting because it's useful for pattern matching for functional languages, for sufficient completeness for term rewriting systems, and in negation in logic programming languages, and so on. But I work with the nominal world, as you know, and in the nominal syntax and the nominal technology, the nominal approach, there is a first order flavor. Although it can deal with the binders, you can express things like lambda calculus, pi calculus with the new. You can express first order logic with for all and exists. You can express languages with binders, but you also have this first order flavor. So we started wondering if we could extend the equational problems that Coleman and Lescan were working on their work and to the nominal world. So for example, in lambda calculus, you know that these two terms are alpha equivalent. Lambda x, xy is alpha equivalent to lambda z, zy. In predicate logic, you know that for all x, p of x, and for all y, p of y are alpha equivalent. But the thing is, you leave these things on the side. You all say, oh, these are the same thing, except for the name of their bound names. And there's no actual mechanics to do with these things. So it's good to work on paper and to think about these things if you can ignore this issue of having to rename or take a new name and things like that. But when you go to the mechanization process, this gives you some trouble. Okay, so the nominal world deals with this. It mechanizes this process of doing alpha renaming and working with fresh names, and it's I don't know if I can say easier. You can work with it in a first order nature. Okay, it's not as difficult as in the high order languages. So if you follow the nominal development, there is now a nominal logic programming language, which is called Alpha Prolog. It's an extension of Prolog. There is a nominal alpha checker, which is based in the nominal syntax. It's called Alpha Check. There is an extension, a library for the nominal abstract syntax for Isabelle. So why not investigate nominal equational problems, since we could try to apply these nominal equational problems to these tools, like in nominal logic programming languages, for instance. So we started wondering if we could do this extension. So before I give you the actual work, I want to put everybody in the same level and give you some ideas of the nominal abstract syntax. So we have nominal terms. I'm going to call them just terms. So terms are defined by this grammar. You have atoms or names. We have suspensions, we have this pi, which is a permutation that is appended to a variable. I'm going to explain this later. You have abstraction, so basically here the name A is bound in T, and we have function applications. Okay, so basically we are going to have two different sets of variables. We have the variables that we want to use to represent the bound variables, and we have the variables that are going to represent the free variables. So the bound variables are going to be represented by atoms, and the free variables, the ones that can be instantiated, for instance, are going to be represented by this big X. Okay, and as usual, a term is called ground if it does not have any variable, the big one, the suspension. So for instance, if you take a signature for lambda terms, you call lum the lambda abstraction and of additive 1, and you have the application of additive 2, and you can represent terms in the lambda calculus as following. You have a variable that this is the one that can be bound, and you have abstraction. Lambda A E means that A is abstracted in the term E, and you have application of two lambda terms. Okay, so the nominal language is very expressive. So you can represent several languages with binders, and you can express pi calculus, as I said. And so once you develop things in the nominal language, usually these things can be reused in several domains. Okay, so I gave you the language. Now let's talk about some constraints. I said that we can represent freshness and alpha equality very easily in the nominal language. So, for instance, I have this freshness constraint. This is the notation for A is fresh for T. What does it mean? If A occurs in T, it has to occur under an abstraction, or it cannot be free in T. So, for instance, in this example, A is fresh for f of B, A is fresh for the abstraction of A in H or AB, because A is abstracted here. B is fresh for this, because B is abstracted in the forall, but B is not fresh for B, because B is free in this last example. In alpha equality, you denote it as equal alpha to T, if the two terms are different only on the name of the bound variables, okay? So, for instance, in these two lambda terms, if you rename A for B everywhere, the bound name A, you are going to get the term on the right. C is free, but it's not a problem because it occurs in the same position in both sides. But you cannot do this third example here, because lambda A application of A and C. Here I'm trying to rename the A, which is a bound name, for a C. But C is not a bound name on the other side. C is occurring free here, and on the other side, C is a bound name. So they are not alpha equivalent, because whereas in one side I have C free, I have C bound on the other side. So basically, alpha equivalent terms, they have to have the same property for all the names. If one thing is free in one side, it has to be free in the other. If it is bound in one side, it has to be bound in the other. Okay, so C occurs free in this term, and observe that C occurs free in this lambda A up AC, and you do not have this property that C is fresh for this term, because to be fresh it cannot be free. Okay, so these things are going to be combined. Freshness and alpha equivalence are going to be combined. Okay, so if you want, when we are working on ground terms, it's quite easy to decide if two terms are alpha equivalent. The problem is when we have variables. For instance, suppose your term has a meta variable, say x. How can we determine if A is fresh for x? Is A fresh for x? X is a variable. I don't know what x is. So basically, we need a property that's going to guarantee that for any instantiation of x, A has to be free. Okay, so for instance, if you are in this P, in this example here, where P is a united predicate, B is fresh for all B, P of X. I can say that this is true, because if B occurs in X, it's going to be captured by this abstraction, so it's going to be bound. So it's fine, because I have this abstraction and the X is in the scope of this abstraction. So it's fine to decide that B is fresh for this term. But what if I have this term? Is A fresh for all B, P of X? There's nothing that says that A is not going to be instantiated, X is not going to be instantiated by X. So you cannot answer this. You have to guarantee, as long as A does not occur free in X, you have that A is fresh for this expression, otherwise you don't know, okay? And the same for these two lambda terms. Lambda A, MA, this is just to say that A occurs in M, is of equivalent to lambda B, Z. You need to see if A does not occur free in Z, okay? Because if it occurs free in Z, you're going to have A free in Z, but A is bound on the other side. So you have A with two different properties. So basically, A cannot occur free in any instance of X in the first case. So we are going to represent this as this judgment. If A is fresh for X, then you can conclude that A is fresh for this expression, okay? And in the same way, if A is fresh for Z, you can conclude that this alpha equality holds. So because of this, we can go to how to implement alpha renaming. So in the nominal language, if you want to check if two terms are alpha equal, we use permutations, okay? So it's easy to see that these two terms in equation 1 are alpha equivalent. They are just, I just renamed A for B in the left side, and I get the right side. But how can we do this mechanically? So basically, we are going to take a permutation here, AB, and I'm going to apply this AB on the left term. So when I apply AB to the left term, well, the permutation only exchanges A for B. So it doesn't do anything in the for all. So I have to pass this to inside of the term. So I'm going to pass this to inside the abstraction, and then I'm going to pass this inside the argument of this predicate. So I'm going to have this abstraction where I replace A for B, and I get for all B. And I have P, and I replace A for B, and I have PB. So I see that if I apply the permutation AB in the term on the left, I get the term on the right here. Similarly, okay, again, we have the ground terms. It's easy to check for alpha renaming ground terms. The problem is when we have variables. So suppose you have, instead of PA, you have a PX, and you want to apply this permutation here, okay? So you do the same. You pass the permutation inside the term, and then you have an abstraction of B, and when you pass the permutation inside the argument of P, you have this permutation applied to X. But you don't know what you have in X, okay? So this is what I called in the language the suspension. I have this permutation suspended in this variable. And when this variable is going to be instantiated, I'm going to execute the permutation and then check if the resulting term is alpha equivalent to for all B, PB, for instance. Okay? So all these things that I said here can be implemented by a set of rules. Okay? So these are the rules that checks if a name is fresh for a term. So basically, if you want to know if a term is fresh for a function application, you check for each term. Of course, you may have variables inside this term, so you might need this context here, nabla, that are like the conditions on the variables that you need to have. In the case you have, this is A fresh for abstraction of AT. A is always fresh for an abstraction on A, so this is a tautology. If A is fresh for an abstraction of BT, you need to see if A is fresh for T. And in the case you have A fresh for a suspension, you have to pass the pi, which is a permutation, the inverse of pi to the other side, and see if the result forms a constraint that is in your nabla. So if you have this condition already in your nabla, you can derive this constraint. Okay, and in the same way, we have rules for deriving alpha equivalence. Okay, so these are equality rules. These are easy. The difficult one is the abstraction B, which is when you have abstractions on different names. So basically, if you want to decide if abstraction AT is alpha equivalent to A prime, abstraction A prime T prime, basically you have to see if T is equal to T prime when you swap A for A prime. Okay, but you also need to be careful because A is bound in T, so it has to be bound in T prime. Okay, so you have to check if A is fresh in T prime, if it does not occur free. Okay, so these are the rules that implement alpha renaming and freshness in the nominal language. So now we don't need to put on the side, just take a representative of your term that has all the things, all the variables renamed in the way that is convenient. We don't need to do this. The system does it for us. Okay, and so now you know some things already. You know the language and you know how it operates, and now we can move to our problem. Okay, so the idea was to extend the equational problems, the first order equational problems, to the called nominal equational problems. So if we want to be fair to Common and Lescan's work, the nominal extension would be an extension of some variables for all of other variables in P, where P now is a nominal system. So we have equations, but now in the nominal language, our equations are alpha equality equations, alpha equations. So we have equations, and we have these equations as they have. But we have a different predicate. We also have freshness. Okay, because when we want to decide alpha equivalence between equations with variables, we need freshness to solve this problem. So we have freshness, and we need negation of freshness, because you are going to see when we want to decide that two things are different. Imagine here, we want to decide here. I want to decide if the abstraction AT is different of abstraction A prime in T prime. When they are different when either this is false, when this is different, or this is false. Okay, A is not fresh for T prime, or you cannot derive that A is fresh for T prime. So basically, we extended the freshness and equality constraints, not extended, we have added the negation of equality and freshness constraints. Okay, and we also work with conjunction and disjunction of these things. The thing is, now we have different constraints. Okay, in addition to the normal freshness, I have something that's called not fresh. Okay, A is not fresh for T, which means A occurs free in T, and S is not alpha equivalent to T. Okay, and we need to deal with these things now. So let's start from the beginning. So now my nominal system has this grammar. I can have true, I can have false, I can have equalities, disequalities, freshness, not freshness, conjunctions, and disjunctions. Okay? And now I can define my problem. My problem is going to be of this shape. This NAP is an abbreviation for nominal equational problem. Okay, so this is my problem now. It looks the same, okay, but when you go inside the system, things starts changing. So, for instance, one application. Because someone could ask me, but where are you going to use this in real life? I mean, it's okay, you can extend first order these equations with binders, but are you going to use it somewhere? So this is one example of a problem which is called sufficient completeness. So we basically want to know if the rules of map completely define map, in the sense that every term using the signature of map, which has F and has map and has cons and L, which is a list, reduced to a normal form not containing map. So for instance, map AF nil goes to nil. Okay, map abstraction of A in F cons. This is for lists, okay, cons of XL goes for the cons of f, where you replace a for x, and what else? And the map of a, f, l. It's missing some brackets here. I don't know what happened. Okay, so basically I want to know if this is sufficient to define the theory of map. So I want to know if there exists f and l such that for all z1 and z2 xl, these equations, this system here, this map holds. Okay, so this is one problem where you have these equations and you have abstractions, and it can be modeled in the nominal language. Okay, so I'm going to present you a rule-based procedure. It has some similarities with the Martelli-Montanari simplification rules, but of course they are extended to the nominal language. Okay, so before I present you the rules, I'm gonna tell you already that these rules are going to be divided into 3 classes. So I'm gonna say that a rule is sound, a sound, because here we need to work in an algebra. So we are working in a nominal algebra, in a ground nominal algebra. So a rule is called a sound in the algebra, whenever an app P reduced to P prime, the solutions of P prime are inside of the solutions of P. It's preserving whenever the solutions of the left-hand side is inside of the solutions of the right-hand side. And it's globally preserving, usually because the rule, there's branching rules, and it's called globally preserving when the solutions of P is included in the union of the solutions of all the branches. Okay? We needed to work with the theory, with the ground theory here. This is still a preliminary work, because when you have that 2 terms are equal, they're equal. It doesn't matter the algebra. But when they're different, they might be different in one algebra, in one model, and not different in another model. So we needed, dealing with the nominal algebra was a bit tricky. So here we only worked with the ground nominal algebra. So we have these trivial rules. These rules are easy. So whenever you have a term equal to a term, you reduce to true. If the same term is different from the term, you reduce to false. 2 names. This is this is a convention, the nominal convention. 2 names, different names represent different atoms. So an atom A cannot be equal to an atom B. A is always fresh for B because A is not occurring free in B. And we have several trivial rules. For instance, you cannot have that A is fresh for T. You can. If you have A fresh for T or A not fresh for T, you reduce to true, because a name is either free or bound in a term. Okay? And if you have the conjunction, this reduces to false. So the trivial rules are trivial. We had to extend the Lescan rules. They only had the rules for equality. For them, trivial rules would reduce to rules T1 and T2. We had to add other 7 rules just to have the trivial rules. Okay? As in Martelli-Montanari, we have clash rules. If you have 2 terms, S and T, and their head have different function symbols, and you are checking for the disequality, so they are different. So this is true. But if you are checking for equality, this is false. Okay? And for a curve check, you cannot have as a variable equal to a term that contains this variable. This is always false. In case you are checking for equality, in case you are checking for disequality, this is always true. Okay, so these rules, we didn't have to change much. We had to add these permutations, append these permutations on the variables because they didn't have this. And also we are working module of equality. These are elimination of parameters. So you can eliminate variables that are not occurring in a system. And this C3 is interesting. If you have an existential on W, and you have W equal to T and P, and this W does not occur in T, in P, okay? So this part of the problem is already solved. You have to solve only the rest, okay? So these are the quality rules. So these are basically where decomposing the rules. So if you have terms that are headed by the same argument, you check for their parameters. If you have, for instance, in E2, if you have terms that are abstracted on the same name, you just check the subterms, check if they're equal. And if the term has two different abstractions in different names, you check if the renaming of one of them, you can apply the permutation in either side. But in case you apply the permutation on the right, ABT is equal to U, you need to check that P is fresh for T, okay? And we also have rules for freshness. So it's kind of easy to see that we are decreasing the size of the problem. So this is useful for checking termination of this, algorithm. The algorithm is basically application of these rules, okay, in the order that I'm presenting here. So we first start applying trivial rules, and then go to clash on occur check rules, and then I go to elimination of parameters. So we have to apply, this is the strategy that we fixed. And then we have, hold on. And then we have, as I said, freshness and equality. These rules are different from the Lescan because they didn't have freshness and they didn't have rules for abstractions, okay? And disunification rules, which is very similar to the previous rules, but now I'm dealing with the to the negation. So, for instance, if you have the difference between abstractions on different names, either when you rename, the two terms are not equal, or the condition of B being fresh for T is not satisfied. Okay, so these are the rules for negation of both predicates. We have rules to instantiate variables. So these are very standard rules. I'm not going to go into details here. And we have elimination of disjunctions. So if you have P conjunction with a disjunction, and one of these P1 or P2 does not have a variable in the forall quantifier, you can just ignore the other one and reduce, okay? And the same for the second elimination of disjunction. And here one example. Let's see one example. It's easier to see how these things work in applications. So let's see. This is a very syntactic example. The interesting ones are too big. So let's take this map, which is for all y, this abstraction lambda ax is different from the abstraction lambda ay. So what I'm doing here, I am going to apply the decomposition rule, which is the one that eliminates the head function symbol, this one. I'm gonna eliminate the head function symbol and check for the parameters, okay? So ft is different from f of u if one of the parameters, the equivalent ones, are different. But my function symbol here, which is the lambda, is unary. So basically, I need to check if abstraction ax is equal to abstraction a lambda ay, and then again, I have the same abstraction, the abstraction on the same name. I can just cancel them and look at to x different from lambda ay. And if you look, well, I'm gonna leave these slides for you. And if you want to look and investigate the rules, you can see that you cannot apply any of the rules that we have before, okay? But we can apply a rule that is in the class of being globally preserving. This is a branching rule, which says, if you have a system with some variables that are existential and some variables that are universally quantified, you can reduce this problem to a bigger problem if you look to, you are increasing the problem, okay? and adding an equation x equal to t. But this variable x is occurring in P, okay? And you have some equation x equal to u inside of P, and you basically are going to move this x from the inside of P to the outside, and check if this x can be equal to a term that you can construct with your language. What kind of terms I can construct with my language? I can construct f of a sequence of variables, I can construct abstractions, I can construct names. So these are testing all the possibilities of T, okay? This is a branching rule, but it is a finitely branching, okay? So this rule is a bit tricky, and it's a problem to prove termination because of this rule, but we managed to find a measure that bounds well, okay? So if you go back to that problem, remember we had this problem for a y, x different from this abstraction here. And the explosion rule is going to do what? It's going to change this problem P1 and make it bigger, adding several equations. It's going to add an equation on x being equal to another lambda with another variable, or x being equal to an application of two variables, or x being equal to an abstraction of a variable, and with the same variable that I had here, a, but I also have to try with another name, and then I'm going to try x being equal to an atom a that occurs in the problem for each atom that occurs in the problem. Here I only have one, so I just have to check one, and I have to check the extend the problem with an equation with an atom that does not occur in the problem. I don't need, that's why it's finitely branching, because I have to check for all atoms that occurs in the problem. The problem is finite, so I have to check for a finite number of atoms, but I have to check it for only one atom that does not occur in the problem. So in the end, I don't need to check for all the atoms in the world, which is infinite, okay? So I branch this rule, and then I have to investigate the possibility of application of other rules from my set of rules. Okay. So what else? This rule here was also a bit difficult to deal. This is a new rule. So basically, we needed to know that we can, whenever we have a conjunction of P with a disjunction of an atom fresh for a variable that is universally quantified. Okay, this is a problem. We had to prove this. We had to prove that this reduced to false. Okay, and A fresh for all y, A fresh for all y is false. Okay, because we were basically saying, is it true that for all y, for all variable, A does not occur free? Okay, in the nominal system, you have an infinite number of atoms, and you can instantiate y in a way that A occurs in y, but you can free in y, but you can also instantiate y in a way that A occurs bound. So it's not true that for all y, A fresh for y holds. Okay, the same for A not fresh for y. And then this is something that we had to prove, and in order to be able to prove this, we needed to find a normal form with respect to the other rules, and to be sure that A fresh for, not fresh for y does not occur here, because A not fresh for y does not occurs here. Then we could apply a trivial rule, for instance. So we had to do some proofs just to verify that we could not get A not fresh for y using different combinations of the other predicates. Okay, for instance, is it possible to have A not fresh for y via some combination of equalities and disequalities? We didn't know, so we had to prove that it's not possible. And what else? Results, okay? results, we managed to prove that this procedure, the application of rules expressed in as R1, R2, R9, which are all the rules that are presented, of course, obeying the order that I presented them. Okay, the strategy is very important to prove termination. So if we follow this strategy, the algorithm terminates. It's in fact an algorithm. And if you have, if you are working in a ground nominal algebra, then the simplification rules are complete for parameterless and definition with constraints normal forms. What does it mean? That you can eliminate all the parameters, and if there is a solution, you're going to find a solution. And definition with constraints is that you can have the normal form as a conjunction of equations, just equations that are irreducible, and freshness and not freshness constraints. So you are going to reach a point where you have only these forms and without parameters, and if there's a solution, you're going to find a solution. You can always reduce a problem to one of these shapes. I didn't want to give you all the technicalities because it's boring. It's huge calculations. And okay, let me see. I didn't ask how much time I had, so 40 minutes.
It's up to you.
Okay. I'm 40 minutes, so I'm fine. Okay, so I'm gonna move to conclusion and future work. As I said, this is a preliminary work. We just finished and submitted this work, and we are expecting some feedback from referees, and we found some difficulties dealing with this freshness predicates and the quantifiers, but at the end we managed to overcome these difficulties. But one thing that we wanted to do is to follow more closely the idea of Common and Lescan, not his per se, of modeling an equational problem using only equality. Okay, here, if, as I showed, we didn't use only equality. We use alpha equality and freshness. Okay, so there is another work. This is the Pitt's definition, Andrew Pitt's definition. It's in his book, Nominal Sets, Names, and Symmetry. He's the father of nominal sets. He has defined the freshness predicate using equality with the swapping, but it's equality. Okay, so basically Pitt said that an atom is fresh for a variable if and only if you can always find a new atom A prime such that the permutation of A for A prime applied in X is equal to X. Okay, so we are trying. The next phase of the work is to go further in the developments and try to be purely equational and see how this new quantifier, this is the new quantifier, okay? It says there's always a new name, a new fresh name that you can get. We want to model these using this approach via fixed point and the new. This is something that we don't know yet how to do because the new, it interacts a bit with the other quantifiers for all and that exists. And it depends where you put them. If you put them in the beginning or at the end, it changes. Of course, it changes the meaning. You cannot move it. So we are not sure how to express the problem well using the new quantifier. So this is something that we still need to work. As I said, we only worked for the ground nominal algebra. So the idea is to extend the result for more complex algebras and also to explore equational theories. We have worked in nominal logic modular, nominal unification modular equational theories for some time now, since, I don't know, 2013. And we found out that we cannot ignore alpha equivalence when we are dealing with operators that commute. For instance, the disjunction or conjunction. You cannot just ignore alpha equivalence when you are dealing with conjunction and disjunctions, because we proved in a paper that it changed the type of the unification algorithm. Okay, so for instance, first order unification modulo commutativity is finitude, but when you work modulo alpha equality, it's not finitude anymore, because alpha equality has some, and the freshness more specifically, has introduced some problems when you have commutativity. This is another work, and if you want to, you can talk about this later. And that's it. That's what I wanted to say. I only put these two references because these are the ones that I use more here, but you can find a paper that I have on nominal disunification only, which was the first step on developing this. And Diane, thank you. Thank you very much.
Thank you very much, Dani. It was a really nice talk. So as usual, we have some time for questions or comments. And I would like just to ask you for manifestation first in the chat to avoid a lot of people talking at the same time. Dani, just a curiosity, have you tried to implement the calculus or check anything with PVS that I know that you like to use?
Not yet. This paper just came out of the oven like 2 weeks ago, so
Okay.
we just did it. We just did it hand on paper, checked proofs. But we need people to do things, to do the proofs for us. I think I see Washington here. He used to do these things for us, but now he finished.
Well,
but this is something that we want to do, but we didn't do yet. Okay.
It would be maybe a nice master thesis to implement this kind of things.
Yes, I agree.
Well, and you told you had some there are some problems about commutativity that you have not talked because it would be too long. Would you like to comment anything about that?
How can I say it? I think if I could, okay, I can show a rule and see if I can bring you with me there. Let's see. Let's see if I can say something. Okay. Imagine, it's difficult, but imagine that your permutation here is AB, and then you have ABX equal to X. B prime is identity. ABX equal to X. And then this rule would say, okay, you just need to check if the domain of your pi and pi prime, which is going to be A and B, are fresh for X. This is in your nabla. And if they are fresh for X, if they do not occur free in X, you are going to have that AB X is equal to X modulo commutativity. For instance, suppose that you take X to E plus F, for instance, E plus, I don't know, E prime. E plus is commutative. And then when you apply AB in E plus E prime, this gives you E plus E prime. It doesn't do anything because A and A prime are not there, so the permutation does not do anything in the term. But the thing is, this is not complete. This is the problem. You are going to miss solution. Just you can have a solution for this ABX equal to X modulo commutativity, even if you have A and B free in X. This is the thing that we miss. For instance, if you instantiate X with A plus B, and then you apply the permutation AB, you are going to get B plus A, and A plus B is equal to B plus A modulo commutativity. And this is a solution that we cannot get with this definition of, we cannot get this solution here, okay? So basically we lose solutions when we look at the rules like that. So the problem is with fixed points. The problem is when we have permutations between variables, equations between variables, and this can give you infinite solutions that are not gathered with the rule that we have now. So we had to develop, we had two different approaches for that. One approach was to leave these equations on variables as output. Okay, so you have these substitutions and you have to solve these equations on variables, find a solution. You give it as output. And the other, this is something that a PhD student of Mauricio is working, it's leaving fixed point equations as output. And the other approach, which is the one that I worked with Mauricio and Maribel, was to define a new predicate called fixed point, that it puts everything together. It gathers all the combinations and it puts everything there. So it's not just fresh, it's all the names that are fixed by commutativity. So we had to develop everything again. And this is a work that we did in 2000.
It take care of all of the variables.
Yes, we took care of everything.
I think about it.
And we didn't leave the equation as part of the solution. We solved the equation, okay? So our output is going to be a substitution as it should be, okay? But because we accumulated all these combinations in a predicate called fixed point, which is, this is something that we did. And I think this could be a very nice approach to work with nominal equational problems in the purely equational approach, using new, because we use new and fixed points, which are equations in this work. So this is something that we want to do, but we didn't do it yet.
Thank you. So Valeria has a question.
Oi, Daniele.
Oi, Valéria. Tudo bem?
Tudo bom. Muito obrigada pela palestra, muito bom, muito interessante, mas eu cheguei um pouquinho atrasada, querida, então eu queria que você, se você pudesse voltar um pouquinho sobre a motivação, eu acho que
claro.
Gostaria de ficar mais
claro.
a par por que as coisas estão acontecendo do jeito que estão.
Claro. I don't know if there's anybody here who does not speak English. Okay, I can explain. It's not a problem. I know Valeria has not a problem with this. Okay. Okay. So I started talking about this paper by Common and Lescan, where they say, okay, we are working with equational problems, and for us and for everybody, an equational problem is a first-order formula whose only predicate is equality. And for them, the equational problem has this shape. It's a sequence of existentials and foralls in a system P, and P can be either equal, different, conjunction, or disjunctions of equals and difference, failure and success. So we started, and I worked a lot with equations and solving equations and these equations, but I solved them not in first order, I solved them in languages with binders. So these problems are useful for pattern matching for functional languages, sufficient completeness for term rewriting systems, and negation in logic programming languages. So if you follow I don't know if you have followed, but the nominal approach is quite convenient because it has this first order flavor for solving equations, but it can deal with binders. You can work solving equation between lambda terms or pi processes or first order formulas. Everything can be, all these languages can be expressed well in the nominal language. So, and the nominal development, the nominal language has been developed a lot, and there are lots of new techniques. And we have now a nominal logic programming language, a nominal alpha checker. There is a library for the Isabel proof assistant. So we started thinking, why not extending equational problems to the nominal world? Okay, so that's the motivation. So basically, we had to show that all those their system of rules or for solving these kind of problems could be extended to this language with binders. The thing is, when you have binders and you deal with alpha equations and renaming of names and fresh new names and things like that, these things gets complicated. Okay, so
yeah, sure. Very, very interesting. But can I kind of then interject a question on it?
Yes,
I mean, I do remember the beginning of the nominal syntax and stuff. I was still in Cambridge when that started with Ian Stark and stuff like that.
Yes, Andrew Pitts was the main person.
And then he had several students, including, as I was saying, Ian and Christian.
And Gabay.
Jamie, Jamie's. So all this kind of, I mean, Jamie, for instance, took it to set theory, right? So
yes, we follow his approach on set theories for looking at the models.
So you see, you already have in your slide 3 or 4 different applications, right? And I was wondering, why do we think that the same sort of settings should be good for all these very different kinds of applications? I'd expect personally, just because, you know, I know nothing about the subject, so, you know, I'm just imagining things here, but I'd expect that things that we do for concurrence theory would be very different than things that we do for functional programming, pattern matching, or for other stuff. In particular, I kind of feel that you know, you're not doing what I wanted you to do if you're not kind of having, I mean, when we're kind of dealing with conjunction and disjunctions, the way, you know, kind of, if we're not being able to do up to commutativity and associativity, then maybe that's
no, you can do. I mean, I understand your question, and this is something that I cannot answer you and tell you that nominal approach is the best approach for to solve your problem. Okay, there are some people that are working on comparing. So there's a paper now where a group of authors have investigated formalizations in 3 different languages for binders. For instance, they have formalized using the nominal approach, and then they're also formalized using, I think, the Brown indices, and then in the nameless approach. They did all the 3 approaches and compared. It's a very nice work. I don't.
That'd be nice. Thank you. I'd love to see
and
that.
they yes, and they compared, and there are things that are easier to do in nominal and things that are not. I mean, it depends on the problem. But there's one thing that's common in all the languages. It is things that you say, look, here you can apply this rule, for instance, in the pi calculus when you have scope extrusion. If this name that the new and P does not occur in the other process, you have P in parallel with Q, and they have a new. If new does not occur in one of the processes, you can put the new inside or outside. But this is in the meta language. You say, okay, if it does not occur, so you do not mechanize it. I mean, so when you want to implement things, you have to take this thing that you do, like, oh, this I'm gonna work modulo renaming. Here I'm gonna take a new name. Here I'm gonna do that. But this is on another level. This is not in the level of your development. And it doesn't matter where you work. You can work in logic. You can work in process calculus, functional programming language. It doesn't matter. You always follow this approach of we ignore this. We just take one representative. So the thing is, we are not in what I'm claiming is, I'm not saying that this is going to be useful for all the things that you want to do, but this specific thing of ignoring generation of new names and renaming of names can be mechanized, okay? And for instance, we have I think Daniele could explain better. He has a student who has tried to formalize things in languages, in lambda calculus, for instance, and he tried 2 approaches. I think he should explain this. I'm gonna tell you because he gave a talk which was very nice, and he compared 2 approaches. He compared the nominal approach, and he compared with the what was the other approach, Danielle? Nameless something, I forgot the name, and to prove something about lambda calculus. And the thing is, if you prove, for instance, that induction works modulo alpha, recursion works modulo alpha, you don't need to do it anymore. You can work modulo alpha and prove everything in your language without having to prove properties again, and whether with the nameless scope, how is it called, Daniele? Let me see, he gave me, I forgot the name of the approach. Locally nameless, yes.
Yeah, you put it in the chat.
Locally nameless. And then he had to keep proving properties about alpha renaming and name generation all the time. So the thing is, for this specific problem, nominal is, well, it's these properties of this, how can I say? You can mechanize this in the language. It's in the language. You can think modulo renaming without having to worry about it. Okay?
May I?
Yes, you can.
May I complement?
Yes,
Daniele?
yes, sure.
Okay, if you want to see some implementation, real implementation of nominal, nowadays you can check the implementation from James Cheney from Edinburgh University. He's a person who is taking the nominal approach seriously, implementing things like the alpha checker and the alpha prologue. Then I think, okay, for say you sequential programming and sequential reasoning, it is very adequate and has been used in practice.
Yes.
Mauricio, who did you say again? You're talking about Jamie again? No.
Cheney, James Cheney. He's from Edinburgh.
A professor at Edinburgh University.
Yeah.
I don't know him, of him.
And he,
an implementer of the.
Yes,
okay,
and the nominal library for Isabel was done by Christian Urban. You know him, right? Yes. So I mean.
Yes, but this is regarding formalization. No, when you talk about Koch and Isabel and PBS, we are aware of and interested in formalizing theorems, but regarding implementations, the person to check is James Cheney.
Yeah. Mm-hmm. Yes.
Okay.
Thank you, Danielle.
Yes. Yes. So, I mean, this is a relatively new technique, right? And the language itself is in development, so we still don't know. We are applying things and seeing and comparing to see how things work. And so the question is, I don't know, I cannot say that this single approach to deal with all these languages is convenient for all the purposes, but you don't need to develop the same thing for each particular language, okay? You could, of course you might need to extend nominal for your benefit, I don't know. It depends on the problem, okay? But you could use the things that we have developed in several domains, okay? If it's going to need some adaptation, probably, okay?
That's fine. That's the. Thank you.
Thank you.
So, any other question or comment? So, thank you very much again, Dani. It was really nice.
Thank you for having me. Thank you all.